Good morning, good evening, ladies and gentlemen. My name is Zheng Guanghou from Institute of Automation Chinese Academy of Sciences. I'm very pleased to introduce our distinguished plenary speaker. We have totally in IJCNN have 7 plenary speakers. Marios Polycarpou, Professor Marios Polycarpou will be the first plenary speaker. So I ordered to introduce Marios. Marios Polycarpou is a professor of electrical and computer engineering and the director of the Chaos Research and Innovation Center of Excellence at the University of Cyprus. He is also a founding member of the Cyprus Academy of Sciences, Letters, and Arts. He received a Bachelor of Art degree in computer science and a Bachelor of Science in electrical engineering, both from Rice University, USA in 1987, and the Master's and PhD degree in electrical engineering from University of Southern California in 1989 and 1992, respectively. His teaching and research interests are in intelligent systems and networks, adaptive and learning control systems, fault diagnosis, machine learning, and critical infrastructure systems. Dr. Polycarpou has published more than 300 articles in referred journals, edited books, and referred conference proceedings, and also co-authored 7 books. He is also the holder of 6 patents. Professor Polycarpou received the 2016 IEEE Neural Network Pioneer Award. He is a fellow of IEEE and hvac, and the recipient of the 2014 Best Paper Award for the journal Building and Environment. He served as the president of IEEE Computational Intelligence Society from 2012 to 2013, as the president of European Control Association also, and as the editor-in-chief of IEEE Traductions on Neural Networks and Learning Systems from 2004 to 2010. Professor Polycarpou is an honorary professor of Imperial College London. His research work has been funded by several agencies and industry in Europe and United States, including the prestigious European Research Council, ERC Advanced Grant, and the ERC Synergy Grant, and the EU Teaming Project. Ladies and gentlemen, please join me to welcome Professor Polycarpou to give us a plenary speech. Marios, please.
Thank you very much for the kind introduction. Good morning, good afternoon, or good evening, depending on where you are. It's a great pleasure to be giving this lecture at the IJCNN. Of course, I had hoped that it would be in physical presence, so I could visit China and enjoy the interaction with friends and colleagues, but hopefully next year. I would also like to thank the organizers of the conference for the invitation to give this plenary lecture. So usually my presentations are mostly on theoretical issues, but today I have chosen to talk about an application which I think is very important in computational intelligence in general. It's an area that is evolving very quickly, and what I'm hoping through this presentation is for those of you that are working on this area to see some of the things that are going on and the new developments and where things are heading, and also for the people that are not familiar with the area of smart buildings, to see an application domain that is very important. It has all the characteristics of computational intelligence. We have models, we have data, and in the future we will have even more data. So let's start by trying to motivate why this is an important area. One of the most important motivating factors is that we spend a lot of time inside buildings. In fact, in the US, an average person spends 87% of his or her life indoors. So it's an important area to see. And when I saw of course, in some other countries, this number varies. But in general, it's true that we spend a lot of time inside buildings. So it's a very important part of our life. And when I saw that, I was kind of surprised. And I thought, well, at least we are spending 13% of our time outside. But in fact, this is not even true, because we also spend, of the remaining 13%, we spent 6% of our time in vehicles and trains and so on. And then we also, the remaining 7% is actually spent outdoors. So it's not very much. It could have been a lecture about spending more time outdoors, but it's not. The lecture is going to be about how do we make our time inside the doors, indoors, which is most of our time, more safe, more efficient for the environment, and create something that is more sustainable using intelligent algorithms. So so not only we spend a lot of time indoors, but also the built-in sector. When you hear people talking about the global energy issues and the green economy, you should stop to consider where this energy is spent. And in fact, 40% of the energy is spent on buildings, in the building sector, approximately, and the remaining 60%, 28% is for the transportation and 32% for the industry. So in other words, the building sector consumes a lot of the energy, and about half of it goes for residential buildings, half of it for commercial buildings. And you can see in the slide where that energy goes to. A lot of it is for heating our houses and offices. Some of it is for cooling. Some of it is for lighting, refrigerator, computers, and so on. But a lot of it goes. So in other words, this is an area that if we can save even 1% in energy, that's a major step towards reducing the use of energy globally. That's one thing. The other thing that is important to consider is, since we spend so much time of our time inside, the indoor environment quality that we have is very important. And when we talk about indoor environment quality, you can think of 4 different things. One is how comfortable we are, so the thermal comfort, how safe we are, how healthy the environment in terms of the air quality. Also, the visual comfort, how is the lighting, and also the acoustic comfort. So all these things are very important. In this presentation, I'm going to be focusing mostly on the thermal comfort and the air quality issues in terms of the quality of air and how do we detect things that might be going on there. But it's important to think that there's actually more than that. So those are the So those are the two things that to keep in mind. When we talk about buildings, one is the energy efficiency, and the other one is the quality of the environment in the building. So those are the two things that are very important. So how is this related to to us? I mean, we are computer engineers, or we are computer scientists, electrical engineers, working in developing intelligent algorithms. How is this related to us? We can think of buildings as large-scale complex systems that are comprised of electrical and mechanical components, different zones, different equipment, and different occupants. So you have people, you have, of course, you may have animals, equipment, in this environment. And also, in order to monitor and control the environment in a building, we have sensors such as temperature sensors, humidity sensors, CO2, occupancy sensors, and we also have a lot of electrical, mechanical actuators like fans, coils, dampers, pumps, valves, and so on. And then we also have a lot of algorithms. We have algorithms to control the air coming in, to control what is being monitored, and so on. So you can see that this is a system not too different from some of the other things that we are dealing with when we have sensors, we have actuators to change things, and we have algorithms to monitor, control, and optimize the operation. Now, a smart interactive building is something that is being evolved. So traditionally, buildings have been in the realm of civil engineers and architects and people like this. But in the new buildings, buildings that are being built, and this is a trend that is going to continue, there's a lot more electronics. This is something important. So you don't see, when you see a building, you only see the walls and the windows and the elevators and things like that. But as time goes by, there's a lot more sensors, a lot more algorithms that are being operated in order for the building to be safe and energy efficient and so on. So you can think of a smart interactive building as a cyber physical social system, okay? Not only cyber physical, but also social in the sense that humans have a big impact on what's going on, where the physical engineering part is the conventional building and the electrical and mechanical equipment, which is large scale and complex. And then we have the cyber component, the cyber core, which are all the communication networks, the computational means, the algorithms, the controllers, the learning algorithms, and so on. So this is the cyber part. And then we have the social part, which is the impact of the human behavior on what's going on, which is important. The social unpredictability, the interactivity, and the acceptance by humans. So whatever we do, humans have to use it. So this is very important. So a smart interactive building can be viewed as a cyber physical social system, which is designed to monitor, coordinate, and control the built environment with the objective to be able to increase energy efficiency and cost effectiveness. So this is an important issue, as we mentioned before, to improve comfort, productivity, health, and safety. This is related to the indoor environment that we have, and increase system robustness and reliability, and finally, increase the interactivity and acceptance by humans.
I think we may have lost Marios. Let's go ahead and see if the internet issue resolves itself.
and air conditioning system is something that is very important for the thermal comfort of the occupants and regulates the indoor air quality as well. So it consumes a huge amount of the building's energy. In fact, 40% of the total energy that is used, approximately 40% of the total energy that is used in a building is used for the heating, ventilation, and air conditioning system. So you can see here, the heating takes most of it, but also ventilation and cooling also takes a considerable amount of the energy that we use. So this is important when we're going to come to look at some of the algorithms that we will develop. So a heating, ventilation, and air conditioning system is basically electrical and mechanical equipment of HVAC systems that are operating 24 hours a day, 7 days a week. And if there's any faults, which happens quite often, this may violate the indoor comfort conditions, as has been shown, and also increase the energy consumption of a building. So it is estimated that we may be losing 5 to 20% of the building's energy consumption because of some of the faults that are going on in some of the sensors, for example, and so on. So at the GEOS Center, at the GEOS Research and Innovation Center of Excellence, we work on different aspects of smart buildings. And today, I'm going to be talking about two of these areas, mainly in the area of heating, ventilation, and air conditioning system, and the indoor air quality. However, there are other applications, for example, with regards to cyber physical attacks, to indoor positioning, to elevator scheduling. So, and I know some of you are working in some of these areas. However, for today's presentation, I'm going to be talking about two of these areas in the area of smart buildings. So one of the aspects that I think is very important, not only for smart buildings, but also for other large-scale applications, is how do we develop algorithms that are more efficient and robust and scalable. So, so the algorithms that we are working on, and I think this is important not only for smart buildings, but also, for example, for large-scale applications like power systems, transportation systems, and so on. A distributed monitoring, learning, and control approaches are becoming more and more important. And I like to stop here and talk a little bit about this because I think it's very important. So when we talk about distributed monitoring, distributed algorithms, this helps to reduce the communication requirements instead of taking everything to a single point. It helps with regards to vulnerability. In other words, we don't have a single point of failure. If everything goes to the same in a centralized, to the same location in a centralized algorithm, then if something goes wrong, then the whole system goes down. On the other hand, if you have a distributed system with many subsystems, if one of those systems goes down, then the other ones can still operate, and I think this is very important. The third advantage is in terms of computational complexity, especially for large-scale systems. Computational complexity is very important. So imagine if you have a system, in this case, a smart building, thousands of sensors that are being available, hundreds of actuators, and all this information has to go through and process in a centralized fashion. So from the computation in real time. So I think this is another important issue, which in favor of distributed. And when we talk about being able to diagnose something going wrong, if we take the example of the large-scale system with thousands of sensors and hundreds of actuators, and we have something that is going wrong. So let's say 5 of the sensors and one of the actuators or 2 of the actuators are not working like they should. Being able to isolate where the problem is a big issue. And once you process all the information in a centralized fashion, it may be very difficult to be able to isolate where the problem is. If you working in a distributed way, then that gives you information. Of course, it doesn't. You still have to deal with the communication between agents and so on, and some fault may propagate from one agent to the other agent, but nevertheless, it's much easier to isolate the problem. And as we will see in some of the applications I'm going to show, compare to the case where everything goes together. And finally, the last issue that I want to mention is the scalability. In the area of smart buildings, but also in other applications, scalability is very important because with the new technology, we have a lot of, we can go to the store and buy new Internet of Things sensors or actuators. We can install them. Everybody's talking about plug and play. And one of the things that we need to keep in mind is that if we are working in a centralized way, every time we add something, we need to reconsider the whole monitoring, the whole control, the whole learning algorithm in a centralized in the main system. On the other hand, if we are working in a distributed way and we have a new zone to add and a new sensor, we don't need to change everything. We just need to modify the subsystems that are connected to the new zone, to the new system. So in this case, we added a new agent, a new subsystem, and from there we have to change only M2, not necessarily all the other ones, because that's the only one that is connected to it. So let's talk about some specific research that we carried out in this area. And the first one I'm going to talk about is the area of distributed adaptive control, or HVAC system. So in the HVAC system, you have control algorithms, intelligent control algorithms that are designed to be able to decide, for the air handling units, what should be the different settings in order to be able for the system to do what we want it to do. In order to design this algorithm, a lot of times you need accurate knowledge of the system parameters, you need precise calibration, and also sometimes historical data. And the idea here was to be able to do that even if you don't have this accurate knowledge. In other words, to be able to adaptively change the parameters of the controller during operation in order to be able for the system to continue to work, even if the system is not known very well, or if it's not well calibrated, or even if it was calibrated and during the operation it has changed due to wear and tear and so on. And let me give you an example. So in this system, the parameters in blue are the controller parameters. Those are the controller gains, and those are typically constant. And the idea is to come up with learning laws so that these are updated during operation in order to improve the performance of the system. Okay, and you can see the details in the paper. It's a recent paper, but the important thing is that we tested in simulation on a benchmark example of a prototype commercial building with 25 thermal zones. This was developed with a very detailed model by Pacific Northwest National Laboratory, and tested it on this. And what we found is that the adaptation that we try to optimize in order to compare with something, try to find the best controller parameter and then compare with that using the adaptive. And the adaptive was able to improve the 7% of the tracking error and almost 3% of the overall energy use, which if you look at it, it may not seem a lot, but when you talk about one of the characteristics of buildings is that the 3% of energy savings is actually very significant, especially for large scale buildings. Let's look at another application in the area of distributed fault diagnosis for HVAC systems. So this problem was formulated. We formulated this problem a few years ago as having the multi-zone HVAC system as a network of interconnected nonlinear subsystems using these equations, and so you can see that the equations are quite complex in general. They have nonlinear components, they have linear components, they have interconnection. Some parts are known, some parts are unknown. And the idea is to be able to detect, in this case, sensor or actuator faults in the system. So the sensor faults that measure temperature, for example, and the actuator faults that are related to the coil valves. So what happens if one or more of these sensors or these actuators fails to operate? How can we detect this as quickly as possible? So in order to be able to do something about it. And the architecture is based on a learning/estimation algorithm that operates in a distributed fashion. Then a detection, some logic that is going on in order not only to detect but also to isolate what type of fault it is. So because of these interconnections, what happens in general is that it may be easy to detect that something is not going as it should. However, it's very difficult to be able to isolate what type of fault it is. So this this decision logic. So you have the estimate of the algorithms that are giving some estimate, and then based on that, if you have some thresholds, and based on some adaptive thresholds, and if the estimate exceeds the estimation error exceeds the adaptive threshold, then you get a 1. Otherwise, you get a 0. Then based on the 1s and 0s that you get a whole bunch of 1s and 0s. Then you have to make sense out of it in order to be able to determine which, among so many sensors and actuators, which are the ones that may be faulty. And this is an important area. For example, when we simulated a 10-degree magnitude sensor fault in zone 10 in this benchmark problem with 25 zones, not only we had significant energy wasted in that zone, but also the comfort of other areas that are interconnected to that area were affected. And in this example, we were able to determine, for example, that we had the detection of the sensor fault that was in somewhat of an automated way is something that is very important. Now we move on to distributed indoor air quality monitoring system. So the idea here is in a multi-zone model of contaminant dispersion to be able to detect areas that there might be a contamination. So you have some sensors in some of the zones, but maybe not all the zones, and a contamination occurs. And how are you able to detect that in a satisfactory way? So this is an area that we worked, and you can see some of the references. Work on the modeling part of it, but also on the partitioning. So if you have a large-scale system, how do you partition it in a way, in an effective way? So the system partitioning. So in other words, if you have a large-scale building, and you have decided to develop a distributed monitoring and learning algorithm, which will be the subsystem? How do you define the subsystem? So a lot of the times, and we also do that in some applications, we are assuming that somebody gives us, this is one subsystem, this is another subsystem, this is another subsystem, and so on. In some applications, it's obvious which one is the subsystem. For example, if you're working with mobile robots, one robot maybe one subsystem, another robot maybe another subsystem, and so on. However, if you look at a power distribution system or a water distribution network or a smart building, it's not obvious which one is going to be the subsystem. So one of the things that you want to do is partition it in a way that is optimized in view of what you're planning to do with respect to distributed monitoring and possibly control. So the way you want to do it is you want to partition it into subsystems while minimizing the weight of the, so you want to ensure connectivity within one subsystem. If something is completely separate, that's the easy case. But if it's connected, so you want to ensure that within one subsystem you have connectivity, and also you want to control the size of each subsystem. So in this case, what we had is one system that was broken into 3 subsystems using this algorithm, and then used to, in this case, the ones that there are contamination in zone 3, 7, and 9, okay? And the ones that are in yellow or orange, depending on how you see it, are the ones that actually don't have sensors in there. So there's no sensors in Z3, Z5, and Z13, okay? So the fact that there are no sensors makes it more difficult to detect, and you rely on some of the interconnections and the models in order to be able to detect those. Okay? So you can see that the algorithm. So what do we mean by detection? The detection means that the residual, the estimation error has exceeded the threshold, the adaptive threshold, and you can see how this happens here. So I have a few more minutes. So in the remaining time, I will talk a little bit about some projects that we have in the area of smart buildings that are somewhat related to some of the things that I talked about. And I'm sure some of you are working in some other applications, for example, in elevator control and so on. So one of the areas that one of my past PhD students is working on, and he started a company, a startup company, is to bridge the gap between research related to Internet of Things enabled components in smart building automation. So in other words, a lot of the types now, so in the buildings we have, in the current buildings, we have building management systems that are closed systems. You know, they're like companies like Siemens and Honeywell and so on develop algorithms that you cannot actually see inside, and they are closed algorithms. So now with new technologies, we are able to go to the store and buy new Internet of Things sensors to put, for example, in my office. I have, because some of the researchers got Internet of Things, so they put them in different locations in the university in order to get data. And so one of the key components is how do you incorporate these Internet of Things devices and build upon the management system, and in order to be able to help with decisions, diagnosis, and KPIs that are related to the system. So this project, the Domognostics project, is to semantically enhance IoT-enabled building analytics and diagnostics in a building. So we developed a platform that is actually able to take information from the floor plans of a building and develop the building, indicate where the you know, if you're buying a new sensor to measure humidity or to measure occupancy, you can incorporate it in there. You can even use through the internet, through the web, to get information about that sensor, and so you can and monitor what's going on. So this is what this does. In another project which is related to the air quality monitoring, the idea is to develop software in order to be able to monitor the indoor air quality in terms of reducing, to optimize, for example, things like the sensor positioning, the estimation of indoor contaminant concentration, detection and localization. And so this is an area that is becoming a lot more important. I know that a lot of people are interested to purchase sensors, especially related to air quality, and installing buildings. And the idea is there's already companies that are selling these sensors. And so the key thing to consider is that once you buy these sensors, how do you incorporate them with the rest of the building management system? And especially if you get sensors from different type of sensors, air quality, related to temperature or flow and so on, how do you incorporate all this and make sense out of it? So this is and finally, one of our recent projects is to relate this indoor air quality with the transmission of viruses. So this is an area, of course, that is very important, and everybody recognizes that the way that the flows in the building are very important on how viruses are transmitted. So the idea is to proactively optimize so in conclusion, the smart interactive buildings is an emerging technology due to the enormous amount of building energy consumption and the urgency to ensure the occupants' health, safety, and productivity. So what I talked about, it just touched the surface of some ideas to develop intelligent algorithms that can be applied in large-scale buildings in order to regulate indoor environment in an energy-efficient manner, to be able to diagnose and accommodate the effects of abnormal events such as faults in the sensing or actuation for the HVAC equipment and so on. And also to be able to detect poor indoor air quality due to contamination events. So this is an area that is becoming more important. It's an area that is very important in terms of computational intelligence, because we have a lot of data, we have a lot of and we're going to continue to have even more data, because the main application, the first application of the Internet of Things would be in areas where you have already established, you have the electricity. So buildings is the area that the Internet of Things is being applied the most. So we're going to be getting a lot more data, and I think this is an area that is becoming larger. Also, it's important to note that the things that I talked about in terms of large-scale systems, developing distributed optimization algorithms, distributed monitoring control algorithms are actually important not only for this application, but for other applications that are actually that have similar characteristics, like a large-scale water distribution network, like power systems, like transportation systems, which have very similar characteristics, even though the models are different, but the approaches are similar. So I would like to acknowledge the research team that I'm working on, which have been so this work that I talked about is in collaboration with other colleagues. Some of them are finished their degrees and postdocs and are now have faculty positions in other universities. Some of them are postdocs and so on. But this is joint work, and it's important to mention that. And before I close, I also like to mention that if some of you are interested in some of them and you're looking for opportunities for either PhD scholarship or postdoc positions or visiting positions, this is something that we can accommodate. So I just wanted to mention, if you're interested, more recently we have also an ERC synergy grant in collaboration with other people from the community, like Barbara Hammer, and we're looking for more highly motivated students and postdocs to collaborate with. That's all that I had, and I'll be happy to answer any questions. Thank you.
Thank you very much, Marius, for your excellent talk. We have a few minutes for questions. There is a question in the chatting pad. Marius, can you see it?
No, I cannot see it. Is it possible?
Okay, I will ask the question. The question is, in all of these projects, is the machine learning used? If yes, what exactly it is used for?
Yeah, so yeah, this is a very good question. So in these applications, there are two components. So in order to be able to achieve monitoring, in order to optimize things, in order to control, you need to use two things. One is you need to use some models that you have. And in this case, there are models, but the models are not perfect. So there are a lot of uncertainty. And the second component is you need to use data, especially in real time. So you need online machine learning algorithms to learn some of the uncertainty in the system, which are not captured by the models, or maybe the models were accurate to start with, but with time they have changed. So how do you use this data in order to improve the model? So it's not the use of machine learning to build from zero, but it's using online.
Marius? Hello, Marius? Can you hear me, Marius?
I think as we come up to the next presentation time, maybe it would be better to invite attendees to visit the virtual platform and post their questions there. And then
Okay.
Marios will be able to answer them.
Okay. Okay. Yeah. Before we close this first plenary talk, I would like to thank Marios for his excellent talk. And also I would like to thank the participants. Please stay with us for the next plenary talk. Next plenary talk will be chaired by Professor Barbara Hammer. Okay, please stay with us.
Can you hear me now?
Yeah, Marios, I hear you now. Yeah, thank
Okay.
you. Yeah, thank you very much for your excellent talk. And there's several more questions. Due to the limited time, we need to go to the next plenary speaker. We thank you very much for excellent talk. Yeah, thank you very much.